Hello, this video is about dimensional analysis. There are two main methods of approaching dimensional analysis. First one is using dimensions, or which is the type of the value, and the second is using units. Technically, the first and the second are the same approach, but they're expressed in different forms. So let's look at the first method of using dimension. Length is often represented as L, time is often represented as T, and mass is often represented as M. So for example, force would be M times L over T squared because M is mass and L over T squared is the acceleration. Energy is M times L squared over T squared because this is mass and L squared over T squared is V squared. Angular velocity is M times L squared over T because angular velocity, which is R cross P, is L times M times L over T, since this is mass and that is velocity, and multiplying this leads to M times L squared over T. Then a question can ask, if force equals to negative kx squared times T, then what is the dimension of K? Force was equal to M times L over T squared, and this equals to K times L squared, which corresponds to x squared, times T, which corresponds to T. Solving for K equals to ML over T squared divided by L squared times T, in which solving this I get T equals to M over L times T cubed. The second method is in fact exactly the same as the first method, but is expressed differently. This time, the values are going to be represented in units. So length would be meters, time would be seconds, and mass would be in kilograms. So force would be kilogram times meter per second squared, energy would be kilogram times meter squared over second squared, and angular momentum would be kilogram times meter squared over second. For example, if energy equals to angular momentum times time to the power of alpha, then energy equals to kilogram times meter squared over second squared, angular momentum equals to kilogram times meter squared over second, and time to the alpha equals to second to the power of alpha. Crossing off the kilogram and crossing off the meter squared value and crossing off the 1 over second, I get 1 over second equals to second to alpha, which means alpha equals to -1 in this question. So I've prepared some questions on dimensional analysis from the recent F equals MA exam, and the first one is question 17 from year 2015. In this problem, there is a flywheel of radius r, height h, mass density rho, and a quantity called tensile strength sigma. And when this flywheel is rotated, this can store kinetic energy, in which the question is asking, what is the expression of kinetic energy stored per mass of this flywheel as a function of r, h, rho, and sigma? Using dimensional analysis, r and h are both lengths, so therefore I'm going to denote it as L. Rho, which equals to mass over volume, equals to m over L cubed, because mass is simply m and volume corresponds to length cubed. For tensile strength sigma, it says this is measured in pascals. And remember that pascals are units for pressure, and therefore sigma can be expressed as F over A. And since force equals to mass times the acceleration, force equals to m times L over T squared. And area corresponds to L squared. And evaluating this expression, this leads to m over L times T squared. I'm going to approach this question via inspection of each options. And for option A, the expression equals to alpha times square root of rho sigma over r, where alpha is a dimensionless constant. So in this case, we can technically ignore alpha. This quantity, square root of rho sigma over r, equals to square root of m over L cubed times m over L times T squared times 1 over L. in which this equals the square root of m squared over L to the fifth times t squared, which equals to m times L squared times square root of L times t. But kinetic energy over mass, this should equal to m times L squared over t squared divided by m, which equals to L squared over t squared, in which for A, the expression does not correspond to kinetic energy per mass. The expression for B is alpha times h times square root of rho sigma times r. Now note that this is h times the option from A, and borrowing the answer that I got previously, the expression in B is simply L times m over L squared square root of L times t, in which this is m over L times square root of L times t. And we see that this is not L squared over t squared, so B cannot be the answer. The expression in C is alpha times square root of h over r times sigma over rho squared, in which this is square root of L over L times m over L times t squared times m times L cubed over m squared. This disappears to 1, and when I cancel out the m and the L, this equal to L fourth over t to the fourth power, in which this is not equal to L squared over t squared. Therefore, C is not the answer. And choice D is alpha times h over r times sigma over rho, in which this is L over L times m over L times t squared times L over L cubed. And canceling out the m and the l's, this equal to L squared over t squared, in which this can be an answer. E is in the expression of alpha times sigma over rho, in which this is m over L t squared times L cubed over m. And canceling off the L and the m, this also is L squared over t squared, in which both D and E can be the answer. But note that kinetic energy is proportional to mass, in which is proportional to height h, which means kinetic energy per mass is not related to the variable h. And this means for answer choice D, where kinetic energy per mass is in the form of alpha times h over r times sigma over rho, this cannot be the answer because in this case, the kinetic energy per mass is linear with height. Therefore, E, which is alpha times sigma over rho, would be the correct answer. The next question from 2018 AF equals MA, question 13. This question isn't necessarily dimensional analysis of comparing the dimensions of two quantities, but instead this is recognizing a certain quantity and simply plugging in the correct numerical value. In this question, it is given that Young's modulus is defined as stress over strain, in which stress equals the force over area and strain equals a change in length over the original length. And the question is asking, what is the Young's modulus of this situation where a person is standing on a rope of tension 7,300 newtons with the original length of 18 meters and it is deflected by an angle of 1.5 degrees. And it is given that the diameter of this rope equals to 2.54 centimeters. Now, stress, which is defined as force over area, would be 7,300 newtons divided by pi times 2.54 centimeter times 100 times 1 meter over 100 centimeter times 1/2 squared, because the bottom quantity is simply pi r squared, or the area of the rope. Plugging this value into the calculator, I get 1.44 times 10 to the 7th power Newton over meter squared. Strain is defined as change in length over the original length. And in this case, since the rope is making an angle 1.5 degrees to the horizon, the change in length equals to 18 meters divided by cosine of 1.5 degrees minus 18 meters. And if this is divided by 18 meters, this equals to 3.43 times 10 to the negative 4. Now note that both the denominator and the numerator are length, and therefore the quantity strain is dimensionless. Therefore, Young's modulus is simply 1.44 times 10 to the 7 Newton over meter squared over 3.43 times 10 to the negative 4, which equals to 4.2 times 10 to the 10 Newton per meter squared. And looking at the answer, E matches our calculation. The next question is question 19. Now in this question, raindrops are falling at n drops per cubic meter, and the radius of the individual raindrop equals to r naught, and the speed of the raindrop equals to v naught. And the pressure from this condition is equal to p naught. Now, if the number density doubles such that there's 2n drops per cubic meter, and the radius is half such that radius equals 1/2 r naught, and the speed equals to 1/2 v naught, the question is asking what is the new pressure in relation to p naught. Remember that pressure equals to force over area, and force was defined as change in momentum over change in time. Momentum was equal to mass times velocity. Total mass of the raindrop equals to n times the density times volume times velocity. And remember that velocity is proportional to r cubed, in which momentum will be proportional to the number density times r cubed times velocity. Time equals to length traveled by this raindrop divided by the velocity, in which this is inversely proportional to velocity. And area, this is simply the surface area of the ground, in which this is not proportional to n, r, or velocity, since these are characteristics of raindrops, not the surface of the floor. Therefore, pressure, which is momentum over time over area, will be proportional to n times r cubed times velocity over 1 over v, in which this equals n times r cubed times v squared. So if p naught equals to n times r naught cubed times v naught squared, then 2n times 1/2 r naught cubed times 1/2 v naught squared equals to 2 times 1 over 8 times 1 over 4 times n times r naught cubed times v naught squared, in which this equals to p naught over 16. The final questions from 2018 F equals MA, question 6. In this question, a rod of length L is fixed at one point, in which it is pulled by a force of magnitude F. And from this force, this rod is deflected such that the perpendicular displacement equals to x. It is given that x is proportional to the force that is exerted. It is also given that x is proportional to the cross-sectional moment, in which it is noted as I, and the unit of I equals to m to the 4th power. And also it says x is dependent on Young's modulus E, in which I'm going to claim that x is proportional to e to the alpha power, where alpha is a dimensionless constant. And it is also given that Young's modulus E has a unit of Newton per meter squared. Since units are given, I'm going to approach this dimensional analysis problem by using units instead of dimensions. The combination of this three relation leads to the fact that x is proportional to f over I times e to the alpha power. And plugging in the corresponding units, this equal to Newton over meter to the 4th power times Newton over meter squared to the alpha power. But since x is a distance, the power of the unit Newton must be 0, in which alpha must equal to -1 in order to cancel out the Newton unit from the force. Therefore, x is proportional to n over Newton over meter to the 4th power times meter squared over Newton, in which canceling out the Newton and the meters, this equal to 1 over meter squared. This means that x equals to some value k times 1 over meter squared, in which this should lead to meter. And therefore, the unit of k equals to meter squared, in which from this we can infer that k equals to L cubed, and therefore x would be proportional to L cubed.